Atmospheric analysis, how much carbon dioxide was in the atmosphere in the Earth's past. So if you get that atmospheric, we're going to set it up first. And then we're going to start to collect some data and get back into the lab. I do believe that the setup part here is important because I think it removes that barrier so you realize how easy these things are to set up for your own classroom, and that hopefully will encourage you to do some of these with your kids. We have made a very deliberate effort to make these as easy as possible to set up. So you as a teacher can walk in and in 10 minutes be set up, ready to go with your class that day. So give me a thumbs up on your screen with the reactions if you have your bag in front of you. And when I see a bunch of thumbs up, we're gonna, nice, good. All right. So I think what I'm gonna do is I'm gonna just play, I'm gonna share my screen.
Bill, is the same one decoding ice cores, atmospheric analysis?
Yep, decoding ice cores, atmospheric analysis. It should have a kind of pop in there. Hopefully Dom's not drinking our club soda this morning.
Yeah, okay. Thank you.
Like, oh man, you gave me club soda. That's awesome.
It's a good mixer.
So again, we are kind of switching back and forth here between teacher hat and student hat. So this is teacher to teacher right now. Let's get this thing set up. Let me share my screen and I will just play the video, and I'll pause it every once in a while to make sure everybody's caught up. All right, I'm here to show you how I like to set up the carbon dioxide direct measurement lab. It makes it pretty easy, pretty quick. To do this lab, you're gonna need some seltzer water. It should not be like Perrier with a ton of minerals in it. Ideally, you want it just with carbon dioxide. All right. I'm here to show you how I like to set up the carbon dioxide. Can you see that video on your screen? Lab. It makes it pretty easy, pretty quick. To do this lab, you're going to need some seltzer water. It should not be like Perrier with a ton of minerals in it. Ideally, you want it just with carbon dioxide in it, and that's it. If it's got a little bit of minerals in it, that's okay. But
Bill, I think the problem is you've got it on your presenter slide.
Deionized water. Okay. Deionized water. Yes, it is. Oh, I apologize for that. I tried to switch some things around so I could look in the eyes today, and I just caused myself trouble. Let me try one more time here.
Did you tell him to have a pitcher of water nearby and the distilled water?
So if you guys could get your distilled water out, you're going to need your distilled water.
The one with all the salt in it?
Nope, the distilled water you're going to need for today, deionized water.
Can I go and grab one? Give me like 2 minutes.
Yep, deionized water or distilled water. And that's perfect, Cal, because we'll just tell everybody we're waiting for you, even though we're really waiting for me.
How much do we need of that?
Just have the gallon out,
Okay.
or whatever you have. And let me try one more time here now. All right, I'm here to show you how I like to set up the carbon dioxide direct measurement lab. It makes it pretty easy, pretty quick. Now, are you seeing the right screen?
What I'm seeing is your presenter thing behind the slide where you choose the screen to share.
Yeah. Boy, oh boy.
Are you,
Good thing.
You got to press the share button, bottom left, bottom right.
Oh, thank you.
now we're seeing,
There
the
we
right-
go.
now we
All
got
right. Thank you very much, Carol. I appreciate it.
it. I think that was Leanne, wasn't it? Or was
Yeah.
it?
All right. All right. So here we go. So we're going to get this all set up. So if you can see the video on the screen there, I have my jug of water and I have a couple. I'll pause it every once in a while to make sure everybody's caught up. To do this lab, you're going to need some seltzer water. It should not be like Perrier with a ton of minerals in it. Ideally, you want it just with carbon dioxide in it, and that's it. If it's got a little bit of minerals in it, that's okay, but just plain old seltzer water works best. You need some deionized water. Deionized water or distilled water. It's usually easier to get distilled water from the store. And when you look at the setup, there's 11 different cores or melted ice cores that we're going to model. We've labeled them already and have our cups labeled so that they're ready to go. If you type out labels like this, makes it nice. You can just write on the cups too. But there's really only two different mixes for the whole lab. One is a 50-50 mix, and one is 10% carbonated water, 90% distilled water. So what I'm going to do is lay out the cores where they go first. Core number 1 is going to be 100% seltzer water. And then core number 2 is 50-50. So I've labeled things up here so I can keep track. So what I'm doing right now is I have on that screen, my left-hand side is going to be all my 50-50 ice cores that I set up. My right hand, I got just a piece of paper to keep it straight in my head. That's going to be the 10% ice cores. And I'm just going to lay them all out. It's going to be core number 2. Core number 3 is going to be a 10% one. Core number 4 is 50-50. Core number 5 is 10%. Core number 6 is 50-50. Core number 7, 10%. Core number 8, 50-50. Core number 9, 10%. 10, 50-50. And core number 11, 10%. So I'm going to put those out there. And you got a deionized rinse water one too. I'll put that up by the deionized water. So you need something to measure 50-50 and 10%. I'm just going to use these graduated cups. It's not completely critical that it's perfectly accurate. So the 50-50 on here, I'm going to go up to 5 ounces, and then I'm going to just estimate up to 10 ounces the rest of the way for my 50-50. So I'll fill up 5 ounces. So right now I am using, I've just labeled what I just wrote on one of my cups. This is going to be 10%. This is going to be 50%. And I'm just using these cups, and I apologize to everybody as you're cringing that I'm using ounces instead of milliliters. I saw the cringe on your faces, which I agree with, but I was just looking when I was trying to lay this out to get 10% and 50%, the ounces seemed like they were a little bit better and easier to use. So I'm gonna
Bill,
yep.
does the volume is a little bit higher because will we be able to fill all these cups with the seltzer?
Yep. So if you
the amount of seltzer?
Follow along with the video here and you should be golden. All right. So watch how much I use. 5 ounces. That's 5 ounces going in the 50-50 cup.
Okay.
And put the rest away up to 10 ounces with the deionized water. And my cups end at 8 ounces, but I'm just going to estimate it's anywhere in the ballpark is fine. It's not real critical. And this one, since it's going to be 10%, I'm going to fill that one to a 1 ounce mark. And then I'll fill that one all the way up to 10 ounces.
Bill, you're saying 5 ounces when the can is 7.5 ounces.
Yeah. So put about 5 ounces in the 1 cup, and then you can fill it all the way up to 10 ounces. And the second cup, the 10% cup, we're going to put 1 ounce in there. Fill the second cup all the way up to 10 ounces. So that's about a 10% solution. And And you should have about 1 to 2 ounces left inside your can when you're done with that.
And how many ounces in the 100%?
But whatever's left in the can is going to go in the 100% cup.
Okay.
So you should have 2 cups at this point. One filled with 50% solution, one filled with 10% solution. Those should be pretty full, ready to go.
When you mean the solution is the seltzer, right?
The seltzer water, yeah. So the 10% has about 1 ounce of seltzer water and 9 ounces of deionized water. The 50% has about 5 ounces of seltzer water and about 5 ounces of distilled water. So you have a 50-50 mix and a 10% mix.
Okay, I missed it.
And again, if you're doing this in your lab, you can get a 2-liter bottle of seltzer water, and then you got a lot more to play with. Louise didn't want to ship you a 2-liter bottle.
Yeah.
So at the end, all these measuring cup, the one that we are actually putting the solutions, they need to sum up to 10 ounces at the end.
Yep, Rose, you're 1 step ahead again. Just as long as you have these 2 cups filled, we're going to play the video, and I'll show you how we fill them all up then.
Well, is the video running? It's not running in my screen.
Nope,
No,
I'm going to start it again right now. Here we go.
Bill, one question I have. So the first one is 100% carbonated water. How much ounce should I put?
Whatever's left in the can after mixing your other solutions, you can dump that into pour number 1.
Oh, so we will go from 11 to 1, right? Like from bottom to top?
Yeah, let me play the video because it's all going to be there instead of trying to do it twice. Here we go. Now I got a big sample of 50-50 and a big sample of 10%. And I'm just going to take that and distribute it between these. Where's 1, 2, 3, 4, 5. And I'll go back and just kind of even them all out. And I'll do the same thing with the 10% one. Even them out a little bit. You want to make sure that you have enough in each sample cup so that when you take your conductivity meter and you put that conductivity meter into the cup, that it actually completely covers the bottom little leads there. So if you need more, you can mix up another batch. I think that'll work for this. We are going to have one more that is 100%. So I'll fill this one with 100% seltzer water. I'll pour that one in there. And then we're going to have one here that's a deionized water rinse. You might want to have a deionized water rinse depending upon how you set up your lab. Like in my room, I put one of these at each table around the whole room. So you might want to have a deionized water rinse at each one depending upon how they go. These, if you're using this kind of conductivity meter, these are a little bit sensitive. So I would have each kid or each group have their own conductivity meter and then travel around the room so that they're making all the measurements with the same conductivity meter. That way the only variable that's changing is the ice core that they're testing. We've had some problems where like you've left a conductivity at a table with the as a lab station, and then the conductivity meters are all slightly different. So you want each group to travel with their own conductivity meter. All right. So now it's just a matter of setting them up around the room. Lab station 1 would be 100%, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. If that was set up around your room, you are
Bill?
sure you have your rinse at each station so that there is plenty of deionized water. And what the students should do then, yes.
The question is, there is no 10 ounces mark on these cups.
Right, it's all pretty forgiving. So anywhere, just estimate where 10 ounces is.
Okay.
Anywhere, it's all very, very forgiving. So it's about 10% and about 50%.
So,
And as long as
but
you're,
but the seltzer is 8%. It came up to 8% in the cup. When I emptied it, it's 8%. 8 ounce, I'm sorry.
Yeah, that's, I
You
need
were
to
supposed
know
to
how
only
many
pour
ounces.
5 ounces in the cup,
Right.
yeah, so in
not
the,
8 ounces. 5 ounces.
Okay. Bill, the number one cup is completed 100% carbonated.
100% carbonated, yes. So number one, anything that's left in your can, just dump it into the cup number one, and hopefully
Okay.
we'll have enough in there. And if not, we'll pretend we do.
No, Bill, I think I missed, I don't know. I'm just confused.
Nope.
Yeah, I'm a little bit confused. How much ounce should we take in each cup? I mean, is there a measurement, or we will assume that the TDS and
Are,
you know
are
the
you, are you
between-
referring to how many ounces go in each one of these ice core cups?
Yeah.
It just kind of divide once you have your main mix, you just kind of divide it between all of the cores that get 50-50, just pour a little bit in each one. You know, you want them about a third full, maybe. We'll do it. So as long as they're all about a third full, you should be good.
Well,
So basically, everybody, we do 2, 4, 6, 8, and 10, 50%.
Exactly. Now you're seeing it. Yeah. See, like half of them all have the same stuff. So once you mix up your master like solution of 50%, you can just take that and pour a little bit in each one of those 2, 4, 6, and 8. Yep. Exactly right.
Matt, Bill, I missed the first step. I think I wasn't here. These 2 cups, one I fill with still water and the other thing with soda. Is that what it is? These 2 cups?
So these 2 cups, one of the cups, you're going to put 1 ounce of seltzer water and 9 ounces of distilled water. So it's a 10% mix of seltzer water.
Salt water, okay.
Don't
Then
feel
the other
bad
one
now,
is a
and I was here and missed it. So
The other one is a 50% mix of seltzer water. So that's 5 ounces of seltzer and 5 ounces of deionized water. And those are your master solutions then that you can just distribute between your ice cores.
Okay.
So yeah, so for ice core 11, so I'm taking 4.5 of ounces of distilled water and 0.5 of carbonated water.
Yeah, but that is one way to do it, but that's why I think it's a lot easier if you just mix up 2 master solutions and then you can just dump them into those cups. Instead of mixing up 11 separate ones all by yourself, if you just mix up a 50-50 mixture,
Oh.
10% mixture, then you can just pour them into all the ice cores.
Okay.
Okay.
Otherwise, you have to make 11 mixtures. This way, you only have to make 2.
Okay, so 50-50, make a mixture of 50-50 and then adjust it to different core.
Yep, and then you put that 50-50 mix, you pour a little bit into ice core, 2, 4, 6, 8, 10. All those get the 50-50 mix. And ice cores 3, 5, 7, 9, 11, they all get the 10% mix.
Oh, fantastic. Okay, thank you.
So that's what I mean. As a teacher setting up, if you just have 2 big beakers in the front of your room and just mix these, takes you no time, and then you can just go around the room and pour it in each one and you're ready to go.
I'm not getting this.
Then we have 50.
Well, I'm sorry.
Yeah, can you give me a reaction on your screen with the thumbs up if you are ready and you got it mixed in your, let me just see how many thumbs pop up.
Use this thermometer to get the temperatures.
We're going to talk about that ready in just a second. It's not
Okay.
not a thermometer. It's actually a conductivity meter. So we'll talk about that in 1 second. We'll talk about that next.
2, 4.
Well, I'm still not get it, please.
Okay. Caldoun, take one of these cups, fill it halfway with up to 5 ounces of the carbonated water, and then the 5 more ounces of fresh water.
Yep. And then 5 ounces, Cal, of distilled water.
Right.
So now, Cal, you've made a master 50-50 solution.
And the other one is 1 ounces.
Yeah, why don't you go ahead and take that 50-50 solution. You're going to pour that, you're going to distribute that to ice cores 2, 4, 6, 8, and 10. So the little cups that are labeled ice core number 2, 4, 6, 8, 10, they all get 50-50 mix.
So Bill, I think we are losing the carbonates in the water.
It'll be okay for the rest of this. Just don't shake it.
So Bill,
Okay.
half of that.
Just distribute it between ice cores 2, 4, 6, 8, 10. I mean, it's, you just kind of pour a little bit in each one. All right.
That's done.
And then you're going to do the same thing with the 10% cup. This one is just 1 ounce of seltzer water, 9 ounces of deionized water, and then that's going to get distributed to the little cups that say ice core 3, 5, 7, 9, 11. So like I said, the first time is always a little bit confusing when you read teacher directions. But I think once you mix it up, it's really just 2 buckets, dump it, set up, you're ready, good to go. All right, while you guys are finishing that, I'm going to switch to which screen I'm sharing here. And I'm going to share this carbon dioxide, and we are going to get ready to.
And Caldoun, I don't know if you've already done it, but the extra carbonated water that was in the can goes in cup number 1 that says age of ice 0 years to present. That all goes, the whole thing, it's 100%.
Thank you very much.
Okay.
Yeah.
I think I missed the first steps that.
Yeah.
What will go in the deionized rinse water? This cup?
Yep,
Yeah.
you do 1 cup with deionized rinsed water as well. Yep.
And how much is that?
Or just fill it up.
So 1 cup with carbonated water and 1 cup with deionized water, right?
Yep,
Yeah.
ice core number 1 should have whatever leftover carbonated water you have. And then you just have the extra rinse cup with deionized water.
Okay.
So the setup should look something like that. That's up on the screen right there.
Okay. Deionized water is to rinse the TD meter. Okay.
Mhm. All right. Now, we are going to do the Cliff Notes version of this with your students. You would test all 11 ice cores. For today, we're going to be doing the Cliff Notes version and only look at ice cores number 1 through 6. So let's do one more little setup check before we start. This is called a, well, let me move on here. Let me stick with the script. So we are going to be doing direct measurements today of carbon dioxide. Carbon dioxide is one of the things that they really go back and look at ice cores for to see how much carbon dioxide was in ice cores in the past. On the left-hand side here is actually how the testing gets done for carbon dioxide. It's drilling in the Arctic, it's bringing them back to the ice cores, it's working in these labs with these expensive machines. All of this is what it takes to really measure how much carbon dioxide was in the past. We're going to instead get you and the kids involved with a much simpler process that models what they do. So when they actually retrieve an ice core, the ice core itself gets cut numerous times. Every single little piece of that ice core gets used for a different part of the testing. So when you look at an ice core, you're going to see this picture a couple times today because we're going to start today testing gases, which carbon dioxide is one of the main gases they test. We're also going to look up, if you look at the top and you looked at your schedule, there's a little slice for isotopes at the top. But every piece of that ice core gets used for something, including archiving. So if somebody comes up with an experiment they want to do in the future that we haven't even thought of, they have some of that ice core left. So when you look at a thin sliver of that ice core, this is the way that your ice core that Louise gave you, that model, is actually fairly accurate. There are visible bubbles of trapped carbon dioxide in the ice cores when you look at a thin section of them. So the strength of that little blue model we gave you is it shows really nicely the trapped bubbles. Now the weakness is our bubbles are a little bit big, but every model has strengths and weaknesses. So that, but I think it is really nice that kids understand this isn't some theoretical thing. You can see the bubbles, and each one of those bubbles has captured the atmosphere from whenever that snow was laid down. So that's why they consider this a direct measurement. This is not any kind of a proxy. This is actually measuring the atmosphere from up to 800,000 years ago. All right, this is the machine that they use. It costs about $70,000 for a used one. This was on eBay, so if you want a used one, you got 70 grand, you can buy your own. Louise could not ship these to you, or this blew her budget out of the water, so instead, we got this for $14.99 for you off Amazon. So this is a conductivity meter. So let me show you again, every model has strengths and weaknesses. Now, if you can buy a gas chromatograph, mass spectrometer, you can measure carbon dioxide directly. Now our $14.99 little gauge here, this cannot measure carbon dioxide directly. However, if you turn it on, if you could all take that little conductivity meter and start by taking the cap off, which is a really important part for students to know. Take the cap off. And Veneer makes some conductivity meters as well. You can do this lab with Veneer. But then when you turn it on, you should see that it starts to read. And we're looking so that on the bottom, there's different scales here. You want the units to be microsiemens per centimeter. A little mu sign, an S per centimeter. Microsiemens per centimeter is a measure of conductivity. So go ahead and turn your gauge on and make sure that it says microsiemens per centimeter.
So click on shift.
Yes.
Yeah, if you're on the wrong units, you can hit shift and it should go to microsiemens per centimeter, and then you're ready to go. And now you're ready to measure conductivity. Now, why do we say teacher to teacher, this is a measure of carbon dioxide? Because that carbonated water has carbon dioxide dissolved in it. The carbon dioxide makes carbonic acid. Carbonic acid conducts electricity. So the higher the conductivity of that melted ice core water that you put in each one of those little cups is a model of melted ice core. The higher the conductivity, the more carbon dioxide it has in it. So now for $14.99, you have a nice little tool that can indirectly measure how much carbon dioxide is in each one of those. And these are modeling melted ice cores, because that's what they do. If they want to see the ice core, they first melt it and then they test it.
So Bill,
Yes.
this distilled water measures 1 microsiemens per centimeter.
I can't quite hear you, Rose.
Huh?
I couldn't quite hear you.
I just measure my distilled water just to make sure it is 0, but it is 1. My distilled water gives the reading of 1.
Yep, your distilled water might have a little bit of conductivity. Sometimes that happens. And that's why I said in that video, it's really important. Everybody has their own conductivity meter, and travel around the room with your conductivity meter, because every conductivity meter is calibrated a little bit differently. Let me keep going so we can collect a little bit of data. In your notebooks on the right-hand side, if you could record this investigable question. This is the question that we are going to go after today. How does the amount of carbon dioxide that you can detect in the Earth's atmosphere change as you go back into the Earth's past? So I think it's important with students who are just beginning in science, and some kids come with a very strong science background out of high school. Some kids come with a very weak science background out of high school. So I think it's really important to kind of have some routines where your eyes go back. I always like to give the kids an investable question like that. And I like to ask them, hey, what do you guys see in this question as the independent variable? What are we going to be changing? And what are we going to be measuring? What's the dependent variable, or what's going to respond? So in this case, it's really easy if you phrase the question in an investable way to say, oh yeah, we're going to be measuring, or the dependent variable is the amount of carbon dioxide, and we're going to have to look further back in time. With ice cores, we do that by drilling deeper and deeper and deeper into the ground. And the deeper we drill, the further back in time we go. So,
Bill, this instrument is just put in the glass and hold it?
yep, we're going to do that next. Ready? You guys are one step
okay,
ahead
thank you.
all the time. So let's get a data table here ready to record some data. Because again, activity before content. Before we start talking about ice core records, we should get kids engaged in collecting data about ice core records. So now that we have a nice, clearly defined dependent variable, independent variable, we can just put those in a data table. And if you want, let's try ice core number 2 now. So go ahead and take your conductivity meter, make sure it's on, microsiemens per centimeter. Let's start with ice core number 2. And all you're going to do, ready, is take your conductivity meter, put it underneath. Make sure that those, we have a little bit. So in this case, you might have to tilt it to make sure it's under the water the whole way. And if you were doing this in your lab and you had a 2-liter bottle, you could use a lot more water. And then just figure out what the conductivity is and write that number down. Mine says 5 for number 2. When you're done, you want to get your rinse water. Get your deionized rinse and rinse that conductivity meter off. Then you're ready for the next one. So each one of those, you're going to do the same thing. Just put your conductivity meter underneath, read the number, rinse it off, and you're ready to go. So we got about 6 or 7 hours today together to do labs. So I'm going to ask that you guys actually stand up a little bit, move around your room. We'll give you about 5 minutes. And we are going to do the Cliff Notes version of this lab. So I'd like you just to record cores 1, 2, 3, 4, 5, and 6. And we're going to stop with the data collection after 1, 2, 3, 4, 5, and 6. And I think we're going to be able to see enough from those trends in the data to move on. So go ahead and take 5 minutes or so and get ice cores numbers 1, 2, 3, 4, 5, and 6. Get readings on each one of those. And then when you're done with that, you can actually make a little graph and we can start to plot these data and see what the data look like. So it is now 9:42. I'll actually give you guys 8 minutes here. You can leave your mics on if you want. If you want to unmute yourself so you can ask questions, talk to each other, do anything else. We're not working in silence. So my clock says 9:42. At 9:50, I'm going to start talking again. Until then, you just have time to collect data. Again, ice cores 1 through 6. See if you can make a graph and plot data 1 through 6 on that graph.
Bill, what's your data for number 2?
Mine was 5. What is yours?
Mine is bizarre because it cannot be a conductivity, that I know. Mine is 58.
58.
Yeah.
Reading microsiemen, if you look at the little symbol there, is it a little small u and s per centimeter?
Yeah. Microsiemens per centimeter. Yeah.
Okay.
Mine is 58 also.
Mine is,
58 also?
mine's high too.
Oh, you know what? Yes, go ahead. Hey, your data is your data. Write your data down. I I don't know if mine is set. I set mine up 3 or 4 days ago. So mine might be completely screwed up by now. So that's one thing teacher to teacher we want to talk about. I think you want to set this up, you know, about an hour before you're actually going to do the lab.
Mine is 40 to 15, like
Sure.
20.
And Permita, yes, or Rose, whoever asked that question, over time, you can see the carbon dioxide leaving that water. So that would
Right.
make sense that yours is 58, mine is only 5. I set mine up a few days ago. I've lost carbon dioxide out of my water.
Oh, okay, okay.
Yeah.
So the
I
ones
apologize.
did the very last, the ones where did the very last has a reading of over 55 because I measured mine in the first time. It was close to 60, 58, 60.
Well, whatever it is, go ahead and write it down. It's just data. Let's not make our data fit our ideas. Let's make our ideas fit the data. And again, all you got to do is collect data on 1 through 6. If you want to keep going, you can, but I'd like you to get to that graph. And we got 6 more minutes, and then we'll come back again. Feel free to unmute your mic and stand up and get coffee while you're doing your lab. And we got a long day of a lot of data collection today, so. Feel like we need some music on in the background here. I feel like maybe Jim should be in charge of pumping in some Hawaiian music to our background every time we do lab time here, just to give us all the chill feeling.
That would be good.
I don't have any. But that's a good thought. I'll
Maybe
try to
during the
rustle
break, I'll
something
get my little speaker. We can choose a genre for each little lab we do today.
So Bill, our highest number is the carbonated one, ice core number 1. That is the present 0 time, right? It is the 0.
I don't know if it's right. If that's what you got, Rose, that's your data. I don't want to be the boss of your creativity. I don't want to be the boss of your data either. But if that's what you got, write it down and let's put it on a graph and see what it looks like. Because that data should tell us a story.
All right.
again, resist doing all of them. We're just doing the Clip Notes version today, 1 through 6. All right. Can you guys give me a one of the reaction thumbs up on your screen if you have some data put onto your graph already? Okay. So we'll give you 3 more minutes. See if you can get some data down on your graph, and then we'll come back at it. Not quite enough thumbs to keep moving.
Well, one of the problem, Bill, is that some of the cups lost the carbonate until we measure it. So we have a little bit discrepancies.
I'm sorry, Rose, what's that question again?
We waited a little longer, so some of the cups lost a carbonated section of it. Maybe the way we pour it, I don't know.
Rose,
You know, we are supposed to have the same reading, right? Between all the 50s.
so,
Or closer.
so you have your readings, whatever they are. See, remember, Rose, we said that this lab is made so that it's really hard to go wrong. So you get your data, whatever your data is, that's your data. We're going to plot it and see what story that data tells. And that data is going to tell us a story that you can then start to talk all about some complicated climate science with your kids.
All right, that sounds fair.
Every kid might get slightly different numbers if you teach the class an hour or two classes back to back. The second class might get different data than the first class, but I think the story of the data is going to tell is always going to be the same. So.
While everybody's working, I just want to throw in that we're having a huge thunderstorm here right now, and this is where the host computer lives. So if it goes off and you suddenly lose School of Ice, just come back, and I think it'll be okay. I can sign up with my phone if I have to and get it started again, but hopefully that won't happen.
All right. So I'm going to ask one more time. Give me a thumbs up if you've got at least 2 or 3 data points put on a graph. And it can be a digital thumbs up or the other. Awesome. Awesome. So we're getting a few more. Good. Okay. So while you're working, you know, carbon dioxide, I think it's really important for your students to understand that when they say carbon dioxide levels right now are higher than they've ever been in the last 800,000 years, that they understand that this isn't something that scientists are just estimating, that they're actually going out, collecting ice, melting the ice cores, pulling the carbon dioxide bubbles out of there and testing them directly. So this is one of the most concrete, well-known, well-documented numbers that we have. We're going to talk about proxies later on today. Those are a little bit, not quite as concrete, but this is as concrete. This is just like going out and measuring the rainfall. It's just like going out and measuring how many tree rings there were yesterday in our tree rings. Concrete data. So I'm going to go ahead and show you. I actually tested all 11 samples, and maybe your data looks something like this when you start to plot it. You do want to connect data point to data point, and I get something that looks like that.
Yeah.
So give me a little thumbs up on your screen there if your graph started to at least look something like that. Yeah. So I think that's awesome. You got a $15 tool instead of a $60,000 gas chromatograph, and you can start to measure carbon dioxide in a melted ice core, which is the exact same way that the scientists do it when they bring back their ice core. They melt it, they test the carbon dioxide, they put it on a graph, and they see what the trends and the stories are telling. So now, this is one way you could start to process it with your kids. We will give you the link to the actual lab, and the lab has some very formal, more traditional questions. But I almost like going this way with these inquiry questions. Again, this isn't my idea. I stole this idea from the New York Times. They had this little activity, 25 graphs that teach about climate change. And this is the type of format they use to teach about these graphs. But they asked kids to just first look at the graph and write down 3 things that they notice about that graph. So I would like you on the right-hand side just to practice processing things a little differently with your kids that open up some wide open conversations. Could you write down 3 things that you notice about that graph, 2 things you wonder about that graph, and then the most important thing that you think that data suggests to you? And we'll give you 5 minutes to do that. It should be 10:01.
I love you too.
Go ahead and ask questions too. It's wide open here. Open your mics up, ask questions.
Hey, Bill, I used just regular filtered water and not distilled. And I'm assuming that that's kind of a no-no, but I figured I'd do it anyways.
Yeah, that Matt's a big no-no,
Yeah.
which is good. I mean, this is good to have teacher to teacher right now. Yeah, it depends on where you live. I can actually get away with it where I live here in California because we have very little minerals in our water out here because it comes out of the snow melt. In Chicago, my conductivity was off the charts when I lived there. So, and I'm guessing in Colorado, depending upon where you get your water from, you probably had really high conductivity. And then that is going to blow away any conductivity from the carbon dioxide. Now, however, Matt, this is how idiot-proof this lab is. I'm guessing that your graph still looks like mine.
It's similar, but the opposite.
Oh, it's,
So like it goes up and
Yes,
down.
yes,
So
it
then
is.
like
yes,
CO
it is. Okay, yes.
CO2 is
Now,
less.
yes, it is. It's opposite without a doubt. Now, here's where I would tell you that you can't go wrong. As long as you have distilled or deionized water. With the seltzer water, like we use pure seltzer water. This is just carbon dioxide and water. So any conductivity, if you had used distilled or deionized water, any conductivity is going to be completely from the carbon dioxide.
Right.
Now, if you can't get this, say for example, you try it with Perrier water, you're still going to get a graph that looks like mine as long as you dilute it with distilled water. But now most of your conductivity is going to be coming from the dissolved minerals. So now it might fall into the category of never let the truth stand in the way of a good story. So, but, you know, like here's when Louise and I did this at AGU this year. This is my wife's favorite little device here, SodaStream. So I just got deionized water. I used her SodaStream and I made my own carbonated water. Then I knew that the only thing in there was carbon dioxide. So if you're a person who doesn't want to let the truth or, you know, want to finagle it all, make it pure carbon dioxide. It works great. just like the 100% seltzer water. You do have to be careful if some, like I said, Perrier is just full of minerals. I mean, it's so high of conductivity, it blows these meters off the chart. So you do have to play a little bit with what seltzer water you're going to use to make it. But yeah, yours is going to be opposite because you didn't have deionized water. So good question. So would anybody share one thing just with open mic night here? Let's just have open mic, and could somebody share one thing they noticed about the graph?
For me,
Sure, this is, go ahead, Rose. Oh, okay,
for
this is
me-
Karen. Oh.
Okay,
Sorry,
go ahead, Carol. No, you go ahead, Carol.
Okay, good morning, everyone. I would just say that there is a repeating pattern.
Nice.
Go ahead, Rose.
For my graph, I noticed the highest concentration right now, present time.
Nice. So you can see.
Uh,
Go ahead. Anybody else?
I noticed spiky curves.
It does. How about things that you wonder about the lab? Anybody throw in something that they wonder?
Why there are ups and downs?
It's a really good question.
Why are the years, why are each cup, why isn't it evenly spaced? Like
Oh,
the years aren't evenly distributed, right? I've been
that is
noticing.
correct. That was very intentional. Very intentional. Yep.
Yeah, Matt, I was figuring that would drive students crazy because then they're equal steps on the graph or equal steps on the graph.
Yeah, you do have to make sure when you're working with students who don't have a lot of experience graphing data that they don't graph the first cup, the second cup, the third cup evenly spaced. That, that's called a line graph. And a lot of times students will use PowerPoint to make line graphs and it doesn't put any scale on it and completely tells the wrong story. But there is a reason why we chose the years that we did, Matt. Yeah. You could go evenly spaced. That would be a nice idea. How about the most important thing? Let's get to the last one. The most important thing. Anybody want to share that?
There's
CO2
natural
is very
cycles.
high now.
I heard from Russ, there's natural cycles. Anybody else here?
CO2 is very high now.
Oh, the CO2 is very high now. It is incredible.
Yeah, mine is the pattern is same, but very little difference.
Okay. See, and that's what I mean, Reddy. It's hard to mess this lab up. The pattern is the same. And
Yeah.
that's the story we want to tell. So I hope you're seeing how this opens up to your class. Before you've really taught any climate science, they're now engaged with really high level questions, observing the data, just like the scientists would. This is the process that real scientists go through when they collect data. They have to go back and just start wondering what story it is telling them about them. They have to start noticing things about the data, and then they start to figure out what the most important thing is. I like processing things this way.
So, one of the School of Ice program, they also link all these up and down readings with the other elements, like they had the sulfur cycles and everything else that they were teaching us. This is a little bit more advanced, but it was very interesting. That pattern applies to a number of things they measure too.
See, and Rose, so I will tell you, we will, we have links, and we'll give you links to all these labs. And all these labs are written up with really traditional analysis questions like that. And Rose, it also has teacher background that talks about all those cycles that drive the carbon dioxide up and down. See, but if you do activity before content, now your kids hopefully are engaged and they want to know what are driving those cycles, instead of just starting off by teaching about all those cycles. So, but these questions are all available, and we'll link these at the end. That is actually on the left there, that is actually the data that the scientists pulled with their $60,000 gas chromatograph and real ice cores. And you can start to see some real similarities between the data we got with our $15 and seltzer water and what they got by going to Antarctica.
Bill, two questions. One is, have you tried this virtually yet with students? I'm curious how that works. And then the second, can you remind me, and I wish I'd remembered, I know, you have 400,000 years, 330,000 years and so forth. That's, one significant figure. How accurate to the years are we? Isn't it like plus or minus like 10 years or something like that?
That's a great question. Eric Osterberg is going to be on later on today, and I would ask that question to Eric. I know their resolution is getting better and better, and I think their resolution in Greenland is better than it is in Antarctica because they get more snow in Greenland, so they have more layers. So one of the activities we did yesterday, Russ, was we tried to count the layers in that ice core, that blue ice core you got. And we talked about when you make direct measurements like that, which counting the years is a direct measurement, we all got slightly different numbers, even though we were counting one little ice core, and they're counting a 2-mile long ice core. So there definitely is some plus or minus with the years. And you can, I would write that down. If you can remember to ask Eric that question when he's on later on today, he could respond to that for you.
You know, just one thing you were saying about the ice cores, Antarctica's resolution and ice cores grew enormously during the International Polar Year because they were able to add ice cores from Dome C and a couple of other shorter ice cores to pick up specific areas in the 800,000 year record that wasn't very high resolution. So the resolution has gotten better and better in Antarctica.
The second part was, had you tried this virtually?
I have not tried it. You're the first group I tried it virtually with. You know, yeah, I don't know. I don't know. I don't know. Yeah, I don't know. I think we have a couple other labs that we could definitely do virtually. And we're going to show you some field trips that are designed later on in this in the School of Ice that are designed specifically to do virtual labs with your kids at home. So we will get into that.
So Bill, when they are taking the ice core, are there any potential damage the experiment, you know, taking the ice core would have on those you know, areas? Like, did they have any risk, or do they specifically select those locations so they don't have that risk?
So I think I would ask you, Rose, to write that question down. And when Eric's on, he's the guy who's been on the ice. I'd love you to ask Eric that question, and he'll be on today at 11:30 my time in California. So depending upon what time you guys are. So he'll be on in a couple hours. But yeah, definitely ask him how they pick those spots. All right, we're not going to do this, and if you want to do it, you can, but now's a great time when you'd come back and you'd use that claim and evidence that we started using yesterday. You know, the data suggests, you know, and I think here you could really say the data suggests that the carbon dioxide level has bounced up and down over the last 800,000 years, and you could put some numbers on that. It's a high of 250 or a high of this many microsiemen, a low of this many microsiemen. You could look at the real carbon dioxide record. And I heard Rose or somebody at Parmita said the data suggests that the carbon dioxide levels are higher now than they have been. Well, that's true. Yes. And you can put some numbers on that. Our carbon dioxide yesterday was what, 415? And usually it's down in the 250 range. So now it's a nice time to put that data suggest and support it with evidence there. All right, I'm just going to finish this up and then we're going to move on. We will make this available to you. We'll put the link up, and Lauren's going to link it to the web later on today. Before we're done, I'd like you to do one more thing for me on the screen. If you could, say goodbye to this activity by taking your meter like this, and I'd like you to all kind of hold it up and just say yes, something like that. And then if you could then hold your notebook up and show me your graph in your notebook, that would be awesome. So let me know when you're ready. There we go. How about on 3, we'll all do it. We'll show it, lean in, put a smile on the right. 1, 2, 3. All right, lean in, show me those meters. Yes. Then show me any graph you got on your notebook. Yes. Oh, those are nice graphs. Oh, look at that. That is awesome. Nice.
There goes the graph.